Hello, everybody. Welcome back. Today we're going to be looking at Unit 6.6, which is all about Introduction to Enthalpy of Reaction. So let's get started. All right, so first of all, let's address this word, this new vocabulary word, enthalpy. Enthalpy is just a fancy word that means heat energy. Okay, but I want you to get used to hearing the word enthalpy more and more rather than just saying heat, but please do know that they mean the same thing. So you've seen this symbol before, delta H. H stands for heat, and delta, of course, means change, and delta H represents the heat flow within some kind of a process. Could be a physical process, could be a chemical process. What we're going to be looking at today is heat changes specifically associated with chemical reactions. And you'll see there that the delta H has a little subscript RXN, that means reaction. So it's just the change in enthalpy associated with a chemical reaction, okay? But it's no different than what we have been talking about. If the delta H of a reaction is positive, that indicates an endothermic reaction. If the change in heat of a reaction is negative, that indicates that it is exothermic. So that's no different than what we have learned. Now, we talked about this a little bit when we looked at energy profiles. And we're going to go into this even in more depth in the next subunit. But the change in heat of a reaction is always the heat of the products minus the heat of the reactants. That's potential energy of the products minus potential energy of the reactants. And again, we're going to see that more in detail in the next unit. So just kind of tuck that into the back of your mind. So the first thing to understand about enthalpy, heat energy, is that it is an extensive property. Now let's review what that means. That means that the value, the change in heat for a reaction, will change depending on how much material you have reacting. Okay, and I always give the example of like a candle burning is a chemical reaction. It's a very small, very controlled combustion reaction. If you put your hand over the flame of a candle, you know, not like in the flame, you're not burning yourself, but you can feel a little bit of heat coming from that candle flame. Whereas if you were to stand next to a bonfire, you're going to feel a much greater amount of heat being released. So small amount of reacting material versus a large amount. Enthalpy changes, that amount of heat associated with that reaction will change depending upon how much material is reacting. In terms of how we are going to see it, that's really going to play into the coefficients that are written in. Okay, so I've given an example here of a decomposition reaction, and you'll see that there is a delta H associated with it. It's positive. And I want you to look at the units. It says kilojoules per mole of reaction. Let's talk about what that means. That means that is the amount of heat, excuse me, the heat change associated as long as those coefficients stay the way that they are. Okay, remember guys, coefficients are just ratios of moles. So that reactant right there is a compound called methanol. If 2 moles of methanol decompose, I will have a delta H value of exactly 252.8. I'll also have that value when 2 moles of methane are created and 1 mole of oxygen is produced. Now, where am I getting these mole numbers? I'm getting them from the coefficients. So when you see the units per mole of reaction, it means the number, that delta H value that you're seeing there is associated with the coefficients that are written into that reaction. So what if I change them? Okay, I want you to look at what I've done here. All I have done is double all of the coefficients. Well, if I double those coefficients, then the change in heat will also be doubled. Okay, because remember, enthalpy is an extensive property. If you change the amount that's reacting, you change the heat change associated as well. Okay, so let's look at some sample problems that address this issue of enthalpy being an extensive property. I'm going to do number 1 with you, and then I want you guys to try number 2 on your own. So number 1 says, consider the reaction below, and I can see I've got a reaction and it is already balanced for me. Suppose 5.41 grams of hydrogen gas is reacted. How much heat would be absorbed or released? Well, here's how I set these up. Every teacher does this a little differently. This is what makes the most sense to me. The way this reaction is written, and I can see that there is a delta H value given to me, I set it up like a proportion. This is the heat associated, and again, per mole of reaction means that is the heat value associated with the coefficients given in the reaction. And for hydrogen, which is the one they're asking us about, there's a 2 in front of the hydrogen. So 52.3 kilojoules is the heat value associated when 2 moles of hydrogen react. What is the heat associated, I don't know, when 5.41 grams of hydrogen is reacted? I'm not going to do this. Okay, I'm going to write this, but don't write it down. Okay, I'm not going to do that because if you'll notice, guys, grams, moles, they're different units. Okay, so I'm not going to do that. Instead, I'm going to I need those units to match up. 5.41 grams of H2, I'm going to divide that by the molar mass of H2, which is 2.0, and that gives me this. Oops. So all I did was take the amount that they gave me and changed it into moles. Did I have to do that? Well, what I could have done, guys, is in this position right here, I could have put 5.41 grams of H2, but changed this part into grams. I could have done that as well. As long as they're in the same unit, it really doesn't matter what you do. Okay? And at this point, ladies and gentlemen, I'm going to put this into my calculator. I'm just going to cross multiply. And the question mark here gives me, let's go to 3 significant figures. Okay, and let's make this sure that this is complete. It said how much heat would be absorbed or released. Well, the value given to me in number 1 was positive, so that's endothermic. That indicates that heat will be absorbed, so I'm going to write that same word. So to me, guys, what makes the most sense is to set these problems up like a proportion. Okay, so I took the delta H value that was given to me, and let's just review one more time. Where did I get that number? I got it from the coefficient. If this problem had been asking us about my product right here, what's the coefficient? It's a 1. So instead of a 2 in my denominator there, I would have had a 1. Okay, so the heat value that you're given is associated with the coefficient, with whichever part of the reaction you're talking about. Okay, so what I would like for you guys to do is look at number 2, pause your video and see if you can do it. All right, let's see how you did. Now, number 2 was just slightly different in that instead of being given a new mass or a new number of moles of oxygen, this time we were given a new heat value. Okay, but I'm going to set it up the same. So I'm going to show you my work here. So if you'll look at this proportion that I've set up, okay, I took the delta H value that was given, negative 1640.1. I put that over top of 3 moles of O2. Now, where did I get that 3? I got it from the coefficient, okay? And how did I know to focus on oxygen? Because later on in the question, we're asked about O2, okay? The new heat value that we were given, 3142 kilojoules, it said is produced, so I went ahead and made it negative. I did my cross multiplication, and what comes out for that question mark, remember it's going to be the same unit as the other denominator, was moles of O2. Now the question asked us for mass, so all I did, I just didn't show my work, is going from moles of O2, I multiplied times the molar mass of O2, which is 32, and that gives me my final answer of 183.9 grams of oxygen. So same process, I just had the denominator to solve for instead of the numerator like up in number 1. So for me, I like to set it up like a proportion. Some teachers like to use dimensional analysis, and you're certainly welcome to do that. It's just kind of your preference. So the last thing that I want to show you here is just, you know, what happens if a reaction is flipped around. Okay, so let's take this line by line. If you look at this line right here, okay, we have, again, we've seen this reaction before, the decomposition of methanol, and there's the heat change associated. It's positive, meaning it's endothermic. Sometimes, ladies and gentlemen, instead of having this written like delta H reaction written out like that, sometimes you'll see the value written directly into the equation, the chemical equation. If you see a heat value written on the reactant side, that is telling you, hey, this is an endothermic reaction. Heat is going to be absorbed as if it's like a reactant. Well, what if you flip the reaction around? Okay, if you'll notice what's on this line right here is just the same reaction here, but written, flipped around. Let's do the same thing. Okay, now the heat is written on the product side, which makes sense. If you flip a reaction around, if the heat was being absorbed as a reactant, now it's being released as a product. And if you think about it, shouldn't it be, you know, I've got these question marks here. Shouldn't the heat of reaction, shouldn't the magnitude be exactly the same? But what's going to be the difference? It will be just negative. Okay. So all I did when I flipped it around was change the reaction from being endothermic to exothermic. Same reaction, same magnitude for the delta H, but now it will be negative. Okay, so occasionally you'll see questions that'll ask you to flip a reaction around and how is the delta H affected. All right, so that concludes Unit 6.6. We're going to get into some of the more mathematical parts of it, some of the more number crunching parts of it in our next unit. So I hope that you have learned a little something today, and I look forward to seeing you next time.